Okay, thanks, Sri. Okay, so yeah, welcome everyone for this verification seminar. So today it's a pleasure to have Prakash Saivasan with us today. Prakash is a faculty member at the Institute of Mathematical Sciences in Chennai. He's done his PhD at CMI, followed by a couple of postdocs at Braunschweig and Kaiserslautern. And Prakash works generally in the area of forming methods theory, I would say. Trying to find algorithmically decide properties of multi-push-down systems, concurrent systems, multi-threaded systems, things like that. Okay, so today Prakash will tell us about verifying programs with weak memory models and persistency. So welcome, Prakash, and over to you.
Yeah, thanks, Deepak. Yeah, so today I'll be talking about verifying programs in weak memory models with persistency. In particular, we will look at a particular kind of weak memory model as presented in a paper, which is a model of a Intel processor. We'll get to that in a minute. Yeah, so the title is loaded with a lot of keywords. So my outline of talk will be first to explain all these keywords. So first I will tell you what concurrent programs are. Then I will tell you what weak memory models are. And I will introduce persistency. And I will tell you what is the verification problem that we are interested. In particular, I will concentrate on a particular kind of weak memory model called the Intel x86 model as introduced by Rad and her colleagues in Popper 22. And we will see how to verify these systems. So what are concurrent programs? So concurrent programs are just, parallel programs that communicate through shared memory. So you have threads. There are multiple threads. There is a shared memory between them. The shared memory can be seen as multiple variables, shared variables. These threads can essentially write or read to this shared memory. I mean, they can write values to the shared memory and they can read values from this shared memory. So let us take a simple example. Most of you might have seen this example before. The Decker's mutual exclusion protocol. So let us say that thread 1 does x equal to 1. Then it asserts y equal to 0. Of course, this will succeed because y is 0 at this point, and it can enter a critical section. And thread 2 writes 1, asserts x equal to 0. But both of them cannot pass this assertion of x equal to 0 and y equal to 0. So in the ideal scenario, these threads, both of them can simultaneously cannot reach the critical section. So what are weak memory models? Well, there are memory models, and it can be categorized roughly into two categories. One is one which has a strong consistency, other which has weak consistency. The strong consistency is usually also called as the sequential consistency. So essentially in sequential consistency, the operations are atomic. That is, you do an operation and you wait for the operation to complete and then you continue doing the next operation. Whereas in weak consistency, these operations can be reordered. So there are examples of this weak consistency. There is the TSO model, PSO model, and the x86 model, the extended x86 model that we will talk about very closely in this talk. So let us first look at sequential consistency. So it has thread and a shared memory, and the rough idea is that the instructions are sequential and immediate. So what are the instructions that a program can execute? It can execute a write operation, a read operation, or it can execute something called a read, modify, write operation, which is nothing but a test and set operation. So what does a write operation do? It just writes a value to shared memory. And whenever this is executed, the behavior is immediate. That is, the write is applied to the shared variable and the write completes. Similarly, the read just reads a value from the shared variable. For instance, here read y would return a value of 0 from the shared variable. And read, modify, write essentially does this read and write operation atomically. So it reads a 0 and changes it to a 2 immediate in a atomic fashion. For instance, here the value of the z variable is 0, and then it gets switched to 2 in a single instant. So the read and write operations are somehow executed in atomic fashion. So, but oftentimes in the modern architecture, I mean, there is a need for speed. So if there is a need for speed, there is also optimization that happens. So there is a very famous peak memory model called total store order. So how does this operate? So now, I mean, I'll give you an operational semantics for this total store order. Is there a question or? Okay. So I give an operational semantics for this total store order. You can think of it as each of the threads or each of the thread in the program has a buffer associated with it called the store buffer, and the writes are buffered. Writes are essentially buffered and reads are immediate in this kind of a consistency model. So what are the instructions here? We have the read, write, the read, modify, write like before. And there's also called something called a memory funds. We'll come to this in a minute. So whenever you execute a write, what happens is it just goes and gets stored into the stored buffer. For instance, the writes are buffered. For instance, if you write x equal to 1, it goes and gets stored into the buffer, and you write y equal to 2, it gets stored into the store buffer. And these writes are non-deterministically propagated to the memory. For instance, x is propagated first and y is propagated next, and so on. Now, a read is either from the buffer or from the memory in that order. So if there is a value that is present in the buffer, then the latest such value is read. Otherwise, the value is fetched from the memory and read. For instance, if there is a read x that is executed by the program, in its buffer, there is a x, write x comma 3. So the value of 3 is returned to the is returned as the value. And for instance, if it was a read z, then there is no z write that is stored in the buffer. So the value is directly read from the main memory.
Right.
Yeah. Hello. Okay. So the total store order also allows you to simulate the sequential consistency using this fence called memory fence. So what memory fence does is it clears out the buffer. It ensures that the buffer is empty before it returns. So yeah, so if you think about it, after each instruction, after each write, if you also ensure that MF is introduced, then you can actually simulate a sequential consistent run using a TSO. For instance, the MF here would ensure that x comma 3 is flushed to the main memory before it returns. So the buffer is essentially empty. The read, modify, write is like before. Now let us look at our Tekker's mutual execution program under the semantics of TSO. So now each thread is associated with a buffer. Now let us see what happens. So there is this x equal to 1. It gets stored into your buffer. There's a assert y equal to 0. There is no y in the buffer. So it goes and fetches this value from the memory, enters a critical section. What does thread 2 do? It does executes y equal to 1. This gets stored into the buffer. There is no value of x in the buffer. So the value of x is fetched from the memory, which is 0. And then it also enters the critical section. Now you see, under the assumption of weak memory, I mean, we have more behaviors, and it is important to verify that the program is still correct under the lax memory or the weak memory model. So this somehow motivates why just checking your program is correct under the sequential consistency is not enough. So there is also another weak memory model called the partial store order. This is somehow more relaxed than the total store order or the TSO. So what this does is it also stores the writes in its buffer, but now the writes are again non-deterministically propagated, but it can also reorder the writes. It only ensures that the writes to same variable are in order. It can reorder writes across variables. So we'll come to this in a minute with an example. So I have some stray zeros in my slides. Forgive me for this. Yeah, so the writes like before are buffered. They are stored into the buffer. For instance, you have these. Now these writes are propagated to memory non-deterministically, but only the writes to the same variable are ordered. So the PSO can reorder writes to different variables. For instance, here the write to the variable Z can overtake or be reordered with the write to the variable X. For instance, here the value for Z is reaches the main memory before the value of X reaches the main memory. Now, if you want to simulate a total store order using partial store order, you can use something called a store fence. So the store fence somehow does not allow you to reorder instructions across it. So if you have a store fence and if you have a write, this write cannot somehow be reordered with the store fence, and the store fence is removed from the buffer in order, in the same order in which it appeared into the buffer. So, for instance, here the Y cannot now reach the memory as long as the store fence is present in the buffer. The other instructions are like before. You have the read, which reads from the buffer, and if the value is not present in the buffer, then it reads from the memory. The MF is like before; it just empties your buffer, and RMW is like in the sequential consistency case. So, why do we have these different kinds of memory models? We saw that the sequential consistency ensures atomic operations, whereas the weak consistency, the operations can be reordered. Firstly, there is advantage for the sequential consistency, which is that it is simple and intuitive, but unfortunately, it is very expensive because some of the operations can take more time. And for instance, the read operation is much more faster than a write operation. So the idea is that the read operations can be performed before the write operation completes. And this is what weak consistency does. It tries to optimize the instructions for efficiency. But unfortunately, this also comes with the complications. Well, if you think of it, the sequential consistency is like our expectations, whereas the weak consistency is like reality. So what we will do now is we will, I will try to explain to you the extended x86 semantics as it was introduced by Rad et al. With slight difference, which I will come to in a minute.
Prakash, I have a question.
Please.
For the store fence, is the RMW instruction treated as a write operation with respect to store fence?
So the RMW by default ensures that the buffer is empty. So the RMW is not inserted into the buffer at all. So the RMW happens only if all the writes are flushed, all the fences are out, and then the buffer is empty, and you can go and directly modify the memory.
Okay.
Is it okay? Okay. Yeah. So I'm not. I did not explain this RMW a bit more carefully because we will not be using it in this talk. Yeah, so this extended x86 has a set of instructions, and more importantly, it has different types of writes.
Prakash, just one question.
Please. Yes.
So if you have a CAS or some such in your program, will it be translated to some fence or RMW, or it will be?
CAS is essentially RMW. So it is a while loop and RMW kind of thing. CAS is compare and shop, right?
Right. CAS is compare and shop.
Yeah.
Okay.
Okay. So in this extended x86 semantics, there are different types of writes. So to each variable, you can either do a WB write, or it is a write back write, as they call it, or you can do a non-temporal write or NTW writes. Now, I have to warn you that if you go and read the original semantics of Rad et al., they have a much more complicated semantics with various other kinds of rights. They have some UC rights, WC rights, and so on. Whereas in our work, in our paper, we have shown that it is enough to consider a subset of all these rights, and you can simulate the other rights using only these specific kind of rights. But I'll come to the semantics of this. So essentially, you have two kinds of rights: a WB right and a non-temporal right, or NTW rights. So both these types are stored in the buffer, in the store buffer. But there is a way in which they are propagated to the main memory. So for instance, here we have a set of or a sequence of NTWs and WB rights in the store buffer. And along with the fence, we'll come to it in a minute. So the NTW rights are somehow like the PSO rights. They reorder with rights to other variable. It does not matter whether they are WB rights or NTW rights. As long as they don't have any right to another to the same variable ahead of them, they can reorder with those rights. WB rights do not reorder among themselves. So the WB rights are like a TSO. So they are somehow ordered with respect to other WB rights, but they can reorder with NTW rights of other variables. They only respect the same variable order. For instance, in this example, we have WBX and NTWZ sitting ahead of it. Then the WBX can actually go to the main memory before the NTWZ goes to the main memory. So there is a reordering of WBX against the NTWZ. For instance, the WBX can go to the main memory. And in fact, there is also a reordering. There can also be reordering among the NTW rights. For instance, the NTWY does not have any right of the same variable ahead of it. So the NTWY can actually go to the main memory before other rights. For instance, here the NTWY can go to the main memory. Now, if you want to avoid such reorderings, then of course you can use fences. You have different kinds of fences. The FL and SF are somehow very similar when it comes to the semantics of extended x86. They don't allow any reordering among the rights. Then you might ask, why do we have SF and FL? I'll come to it in a minute. And FO also reorders with other instructions, and it only cannot reorder with a SF or earlier write. So later write can reorder with FO, whereas it cannot reorder with the earlier executed write. Now, why do we have this FL and FO? FO, by the way, has no meaning or no semantics, or it has no behavior in the extended x86 semantics, because these two are only relevant when persistency is introduced. These are persistent fences. So when we come to persistency, you will see why these are required. In fact, I will not be talking about this SF-FO combination because it's a bit complicated. I will only talk about the FL persistency fence when we come to the persistency part. Okay, let us now introduce persistency. So what is persistency? So you can think of it as a two-layered architecture. You have a memory model and you have a persistent system. The persistent system somehow is used to archive your writes. So the persistency archives the writes from that reaches the main memory of your original system, but not necessarily in the same order. So it can do some optimization. It can reorder the incoming writes. So any writes that are applied to the main memory is also visible to the persistency system, and it can do some kind of reordering, and then it tries to persist these writes. And of course, there are some fences like we saw the FL and FO, which can be used to impose some ordering on how it persists these values. So why is this persistency useful? So the persistency is useful in case of a crash. So if there is a crash, the value that the so you also have a persistent memory. The value in this persistent memory is copied onto the main memory, and the computation is restarted from that point on. So in case of a crash, this persistent system becomes useful. So what we have done so far, we have introduced this x86 model and persistency. Oh, we have not introduced the semantics of this persistency model. Okay. With respect to this x86 model, let us see what is visible to the x86 persistent system. So the instructions that are visible from the x86 memory model to the persistent system are the writes and the fences of it. And this x86 persistent system, if you recall, I said that it can reorder instructions. So it has a buffer of its own, which we will call it, which we will call as the persistent store. So what are the instructions that are visible to this persistent system? It is exactly the writes and the fences. So you have the different kinds of writes, the WB writes and the NTW writes. You have the FL fence and SF and FO, SF and FO fences. Now, what happens if WB write is visible to the persistent system? So when I say visible, whenever it is applied to the, okay, I have a question in the chat. Does the model have a cache in between store buffer? Okay, so somehow this is an implementation detail. I do not know how this model is implemented in the system. So I mean, I'm not competent enough to answer how in the architecture it is implemented. As a model, we do not have anything between the store buffer and the persistent store.
Okay,
I hope this
thank you.
answers.
Yeah, thanks.
Okay, so where were we? Yeah, so suppose, so when I say a WB write is visible to the persistent system, it means that it has reached the main memory of the memory model. And when that is visible to the persistent system, what the persistent system does is, it just buffers these writes. So for instance, whenever there is a WB of x comma 2, it just puts it in the buffer and so on. And the only ordering that it maintains among these writes is the variable specific ordering. That is, all the writes to a particular variable are ordered, and across the variables they can be reordered. For instance, the y comma 3 can reach the persistent memory before x comma 2, and so on. Now, what happens if you have a NTW write? An NTW write directly persists. The moment it reaches the main memory, it also reaches the persistent memory. But in some sense, the NTW instruction waits till all the writes to the same variable in the buffer are flushed, and then rewrites, or it ensures that it persists and then returns. So essentially, whenever an NTW to a variable, NTW write to a variable is applied to the main memory, it ensures that there are no other pending writes on that variable in the buffer. For instance, here it waits for the write to be flushed to the persistent memory, and then it persists this current write and then returns. What does the FL flush do? The FL flush essentially ensures that there are no pending writes to that variable in the buffer. Essentially, it is like an NTW without a write in the end. So it just ensures that there are all the writes to that variable are flushed to the persistent buffer. Well, Dhruv has a question. Every thread has its own buffer. Is that also the case for persistent buffer? Well, you can look at it that way. I mean, again, this is the model that this is an operational semantics that Rad et al. Proposed, that there is a single buffer. Again, I do not know how it is implemented in the architecture. I believe there is a single buffer also in the architecture, but in our model, there is a single buffer in which all the Okay. So here there is no concept of thread. So the persistent buffer is common to all the thread. It is outside the system. It does not, it knows about the threads, but it is outside the system. So there is one persistent buffer in the persistent system. So it is not thread specific.
Oh, I see. So there can be interleaving between two different writes to two different threads.
Yes.
In
So,
the persistent buffer.
Yeah. Yes, there
Uh-huh.
is. Yes.
Okay.
Yeah.
I see. Thanks.
Yeah, sorry, I misunderstood your question. Yeah. So the persistent system has a single buffer, and there is no connection between the thread buffer and, per specific thread here. Okay, so where were we? No pending writes. Okay. So yeah, we were looking at this FL. So FL somehow ensures that all the writes stored in the buffer for that particular variable is flushed. And yeah, FL is this. Then the SFFO is a bit complicated semantics. What it does is the FO is stored in the buffer, but along with the tag of which thread executed it. And whenever an SF is executed, it ensures that there are no FO for that thread still pending in the persistent buffer. So easier way to think about it is the SF and FO combination ensures that all the prior writes by that thread are persistent. So, this is all I will say about this SFFO combination. We will not be, the semantics is a bit complicated, so we'll not go into it in this talk.
Prakash, just 1 minute.
Sure.
Sorry. Deepak, can you also give someone else the, can someone volunteer to record?
But if you record, it still records if you exit, is it? Or does it not?
No, I don't think so.
Okay.
Okay.
Deepak, will you be
Alvin, are you able to record?
Who? Me?
I'll just ask Alvin.
Yeah. Let me see.
Okay, I'll just make you co-host then.
So I'll continue this, but just in case.
Okay, take.
So, sorry, Prakash.
Okay,
Sure.
let's go ahead.
So do I record to the computer or to the cloud?
I think to the computer, yeah, to your computer.
Okay. Got it.
Okay,
Thank
let's go ahead.
Yeah, thank you. Sorry.
Yeah, so we will not be explaining, or I will not be explaining the SFFO combination any further. So what is the problem that we are interested in? The problem that we are interested in is this. So you are given a concurrent system, you are given a specification, a correctness specification, and we ask whether the system satisfies this specification. So for instance, the specification could be mutual exclusion, like in the program that we saw earlier, whether two threads can simultaneously enter the critical section or not. So for the purpose of our talk, we will only be looking at safety specifications, which usually translates to reachability in your system. So what do we know about the classical memory models that have been well studied? Sequential consistency, the verification problem is p-space complete. For TSO and PSO, the complexity is non-primitive recursive. And in particular, the decidability goes through theory of well-structured transition system. So what we are interested.
Prakash, so the
Yes, please.
programs, what kind of programs are these?
These are the normal programs like what I showed you. They can do a read write. No, they can have they can have loops. They can have they don't have recursion, but they are. They don't have infinite data, but they can have branching.
So okay, so you can have loops and things, is it?
Yes, you can have. Bounded loops, for instance.
Okay.
Yeah.
Okay, let's go ahead.
So what are we interested in? We are interested in reachability in presence of crashes. So what does this mean? So what happens when a crash happens? So you start from an initial configuration, you reach a configuration with a particular persistent memory, then a crash happens. Then what happens is the persistent memory is copied to the main memory and the execution continues. You reach another persistent memory, then a crash happens. It is copied to the main memory and continues. And in the end, from some persistent memory, you reach a final configuration. So the persistent reachability problem asks whether you can reach a particular final configuration in presence of crashes. So if you look at it, there are two aspects to this reachability problem. One is whether you can reach a persistent memory, and from some persistent memory in the from some main memory which contains a reachable persistent memory, can you reach the final configuration? So there are two aspects to it. One is whether a persistent memory can be reached, and whether a particular configuration can be reached in the crash-free setting. So if you can solve these two problems, then the persistent reachability problem can also be automatically solved. So we look at these two, how to solve these two individual problems. That is whether a particular persistent memory can be reached, and whether a particular final configuration or a state reachability can be performed in the x86 or Intel x86 semantics in the crash-free setting. So these are the two problems that we will focus on.
Question, Prakash.
Yes.
Sorry, can you go back to that slide?
Okay, just a
Oh,
minute.
sorry. So, I mean, I just want to know, when you write initial plus M1, you mean you'll start
Yeah.
like
Yeah.
what does initial plus M1 mean? It's like you will start.
I will have the there is a main memory component in your memory in your weak memory model, right?
Mhm.
So that is replaced with the persistent memory.
And what is the initial there? Like, is it?
So initial is buffers are initialized to 0,
Okay,
and
okay. I
the
see.
state each
Okay,
of the program starts from initial state, for instance.
No, so all the, oh, I see. So each program will start from its initial state, is it?
Yes.
Okay.
But then looking at a different memory configuration, they can do different things. I mean, in the initial configuration, they would have done a different behavior. They could have had a different behavior because it was an initial memory. Now they can have a different behavior because the memory is different now.
Correct. No, the question was like, I mean, so each program is now restarted from its initial.
Initial.
Okay.
Yes, I mean there are various ways you can do. You can see it. It's all equivalent. You can also change the state of your initial. You change your initial state based on this. Persistent memory reach. But for simplicity, we'll assume that it all starts from the initial state.
Okay. Thanks.
It's all equivalent. I mean, it can be encoded for.
I see. Okay. Thanks.
Okay, so I hope the problem that we are interested in is clear. So we want to verify these x86 programs in the presence of persistency. So for this, what we said was we want to look at two different problems. One is the persistent memory reachability and the crash-free reachability. So persistent memory reachability is whether we can reach a particular persistent memory configuration, and cache-free reachability is whether we can reach a state, whether we can reach a program location in presence of no crashes. Okay, first we look at this persistent memory reachability. By the way, the contents of rest of my talk is based on our paper, which was recently published in PLDA. Okay, what is this persistent memory reachability? So the persistent, so the way we solve persistent memory reachability is that we show that the persistent memory reachability can actually be reduced to crash-free reachability, but in a different program. So essentially the figure is like this. If you give me an original program and I want to check whether a persistent memory can be reached in this original program, I write a new program. And then in this new program, I check for cache-free reachability. So the reachability is preserved across this translation. In fact, what we do is we introduce a new program called the manager program. And we also we show that we can actually do a code-to-code translation of each of this original program into the new program. And in this new concurrent program, the the crash-free reachability solves the persistent reachability in the original program. Okay.
So one question. So is
please.
P1, P2, like, are they instances of the same programs? Are they different programs? What is
No, they are different programs. They can have different code. They are not instances of the same program.
I see. And the manager manages all of the different programs.
Yes. Okay. So
Okay.
maybe P was not the right rotation. T1, T2. Just replace it. So they are thread 1, thread 2, thread 3, thread 4.
I see. Okay. Thank you.
Yeah. So how do we go about creating this new program? The rough idea is this. So we employ a guess and verify technique. So if you look at what persists, it is actually a write that persists. So a write that reaches a main memory actually persists at some point in the persistent system. So the manager guesses that this is the write that is going to persist. And then once he guesses that this is the write that is going to persist, what he needs to verify is that there is no other write that actually pollutes this guy. That is, no other later write persists on top of this. This is what he needs to verify. So essentially, the manager guesses the write that will persist last and ensure that the guessed write is not overwritten by some other write. So this is what we call as the guess and verify technique. So first of all, the idea involves manager speculating a write that will persist. But you see, if the threads write directly to the main memory, the manager cannot observe all the writes. He can miss many of the writes. So he will not even know that a write has happened. So what we do is we introduce per process memory. So essentially we copy this main memory for each thread. So there is a per thread memory probably. I mean, I don't know why I use process and thread. I mean, rewrite all the process in your mind as threads. So introduces for each thread a copy of this main memory. And then these threads now write to their copy instead of to the main memory. And the manager is one who is responsible for transferring the contents of this copy to the main memory. So now manager has with him, or manager can see almost all the writes. He still cannot see some part of the writes, but this will not be important. So what he cannot see is if there are writes to the same variable, he cannot distinguish it. He cannot he will not be able to distinguish multiple writes to the same variable. So, but when he is copying, he needs to ensure that the update order is maintained. In particular, if there is a write to X followed by write to Y, he cannot write to Y followed by write to X. But this we can ensure by ensuring that there are no updates during a copy. So during a copy, so he copies a value from one of the variable to the main memory and ensure that at the end of the copy there are no more updates to any of the variables, any of the copy variables. Yeah, so we also have to take care of the thread reads. So now the threads cannot read I mean, threads have to be a bit careful when they are reading. I mean, they cannot directly go and read from the main memory if they already have something in their buffer. So what they do is they read first from the copy and then from the main memory. If they don't find the copy, which means that it is not there in the buffer or in the local in their copy of the memory, then they can be sure that they can go and read from the main memory. And since the manager now has handle over the writes, he can pick a write non-deterministically, and he can mark it as to be persistent, or that will be persistent. But unfortunately, I mean, this alone will not solve the problem. He also he needs to ensure that, so first of all, he has to do this for each of the variables, and he needs to ensure that at the end of the run, this value is not overwritten by some other write. So for rest of the talk, what I will do is I will give a name to pick a write that will persist. So if the manager has picked a write that will persist, I will call it the frozen write. So how does the manager verify that the frozen write is not polluted, or it is not overwritten by some other write? He does this by ensuring that certain bad patterns don't happen. So these are called the spoilers. So the manager ensures that these are the only bad patterns that can spoil the persistent memory, and he ensures that none of these bad patterns occur. But he alone cannot do this. He needs the help of the thread, as we'll see in a minute. Let us say that there is a write which he marked it as the persisting write or the frozen write. Now, what happens if later NTW write hits the main memory? The NTW, if you remember the semantics, will overwrite the write in the persistent memory immediately. So this bad pattern has to be avoided. This NTW write cannot reach the memory or cannot be executed after a write is frozen. Similarly, this we call as the NTW spoiler, but unfortunately, this has a problem associated with it, that the manager can miss the NTW writes, especially if it is followed by a WB writes. Even if you want to mark these NTW writes by a new value, these NTW writes can be, it is the WB writes that follows it can overwrite the value that you mark, for instance. So for instance, there was this frozen write followed by a WB write. Then after that came an FL. If you remember, the FL will flush all the writes that are pending in the persistent buffer. So this WB write will be flushed to the persistent memory, and hence this will pollute or this will rewrite the frozen write. So this is another bad pattern that you need to avoid. There are other bad patterns that I do not go into, especially the SFFO bad pattern is a bit more complicated to handle, but let's see what we can do with this. So there is again a problem here. So this is called the FL spoiler, but the manager cannot observe an FL operation. FL operation is a fence, so he cannot observe the FL operation. Yeah, so there are other spoilers involving FO, which is a bit more complicated. We'll not go into it in this talk. Now, how do you detect the spoiler? Well, I will give you only a very high-level overview of how we detect these spoilers. Each thread speculates a position, or called the freezing point for each variable. And it tracks the potential spoilers after this freezing, after this position that it has speculated. The manager, on its part, verifies that the speculation is correct and ensures that the spoiler that the thread has seen and is trying to report is never seen. So it can be in its buffer, but the moment the spoiler reaches or is visible to the manager, it is actually a spoiler. So it is not a spoiler as long as it just remains in its buffer. But there is a problem here also. I mean, you cannot just speculate a position and then write. You cannot write a flag saying that this is the position for the freeze, because there are reorderings. Especially there are the NTW can reorder with other writes. So, I mean, I will not go into how we solve this problem, but for interested readers, I would urge them to go and look at our paper. So what is the moral of the story? The moral of the story is this, that the persistent memory reachability can be reduced to cache-free reachability. But we still have cache-free reachability to handle. So what was cache-free reachability? Without the presence of cache, can we reach a particular state in the EX86 semantics? This is the problem that we are interested in. Okay, what is the question? So the suspense here is, unfortunately, cache-free reachability is undecidable. So the reduction is from a well-known post-correspondence problem, which is known to be undecidable. And the crux of this reduction involves the ability to perform alternating bit protocol. So I will briefly explain to you what is alternating bit protocol that we use using these two threads. This was too fast. Okay, here. So the thread one repeats WB x equal to 1, writes WB using a WB writes x equal to 1, y equal to 1 n times. Of course, this is not somehow restricting. The thread can immediately execute this n number of times and then store everything in the buffer. The whole interesting part is in the thread 2. So what does the thread 2 do? It first asserts that x is 0, and then it waits for this update of x equal to 1. It tests and set 1 to 0. Then it ensures that the y equal to 1 has not reached the memory by asserting y equal to 0. And then tests and sets y equal to 1 while asserting x equal to 0. But let us go over this example a bit more carefully. So initially the value of x is equal to 0. So thread 2 can do assert x equal to 0, but he cannot do a RMW of x1 to 0 because the value of x is still 0. So he waits for the update of x equal to 1. So the x equal to 1 reaches the main memory. Then he can execute this RMW and change from 1 to 0. But then if the y equal to 1 also reach the memory, then he cannot perform the assert of y equal to 0. So the only way the program thread 2 can proceed is if there was no update to y. So at this point, there was no update to y or update of the right y equal to 1. And then the assert of y equal to 0 succeeds. Then he waits for the next update to y, which can happen, and then he rewrites it. And he ensures that there was no other update to x immediately by asserting x equal to 0. And in this way, what we have is the thread 2 reaches the end of the program only if it did not miss reading any of the writes. So this is the alternating bit protocol that we employ to show undecidability. So what is this PCP problem? So you are given some set of ordered vectors, ordered words, and then you are asking whether there is a sequence or a sequence of indices such that, or a sequence of indices I1 to IN such that UI1 dot UI2 dot UIN is equal to VI1 dot VI2 dot VIN. So essentially what you are asking is whether you can pick a sequence of words from U set and the same sequence of words from V set such that both the words if concatenated are the same. So what we show here is that we can actually reduce this problem to cache-free reachability in a particular program. This program contains these two threads. It contains a PCP generator and a PCP verifier. What this PCP generator does is it tries to generate a solution for this PCP instance, and verifier actually verifies whether the solution is correct or not. And in this process, we will be employing this alternating bit protocol in this reduction. So how is this alternating bit protocol used? So what does the PCP gen do? So he just picks an index and then writes the corresponding words to two different variables using a NTW write. Recall that NTW writes can overtake each other if they are not to the same variable. So this S and T somehow can reach the main memory independently. This UI and VI can reach the main memory independently. And what does TCP gen do? He also encodes the size of how many symbols he has written to S and T as an alternating bit protocol. So he writes a WB write of X equal to 1 and Y equal to 1. And what does the verifier do? The verifier, first of all, by employing alternating bit protocol, ensure that no symbol is lost. And he also verifies that the words generated are the same. So he ensures that each symbol in S and T that he reads is actually the same. Krishna asks, is it without RMW, is it decidable? Well, I mean, yes, it is not decidable. Even without RMW, we can show that this problem is not decidable. Just a minute. Yes, yeah. So, yeah, I had, okay, let me just think for a minute. Yes, so, yeah, essentially it is undecidable even in presence of no RMW. So this is the answer, but we can discuss it offline.
So these UIs are numbers, UIs and VIs are what, numbers?
No, these are words. So UIs and VIs in this PCP are words. And then you are asking whether there is a sequence of indices such that,
in the program, in that PCP gen program?
It is okay, this is a abuse of notation. So this is writing these words one by one to S, writing the letters in this word one by one to T. So this is a bit of abuse of notation. Is this okay?
Yeah, okay. So,
yeah, so
basically strings, is it? This
yes.
S and T.
Yeah, S and T are variables. And this UI, for instance, if it is A1, A2, then you write A1 to S and A2 to S. Similarly, if this VI was B1, B2, B3, then you write B1 to T, B2 to T, and then B3 to T.
Okay.
Yeah. Okay, so what is the moral of the story? The moral of the story is that crash-free reachability by itself is undecidable. But we have a decidable fragment which is decidable. I mean, which we show that there is a fragment which we show that is decidable. So what is this fragment? We call it the alternation bounded reachability. And what is the intuition behind this? One source of undecidability is there is an unbounded alternation between the NTWs and WBs in the reduction that we saw earlier. So then what if you bound the number of alternations between these NTWs and WB writes? So this is the intuition. So we define a K alternation bounded execution of thread. We say a thread execution is K alternation bounded if it alternates between WB and NTW a bounded number of times. So for instance, if this is a run of a thread, it alternates between WB and NTW at most n times. So this is a n alternation bounded execution of this thread. Now we ask whether a final configuration can be reached by an execution in which every thread at most makes K alternation. So this is K alternation bounded reachability that we ask. That is, whether we can reach from the initial configuration to final configuration, where every thread plus at most K switches between WB and WB to NTW. So this is the question that we ask. So I hope the problem here is clear. Okay, so we show that this problem is actually decidable. So, but there are difficulties even here. So if you see, so let me call these blocks. So this is the first block, this is the second block, and this is one alternation. And then this is another block, and this is another block. in the second alternation. Now a write from this fourth block can potentially overtake all the writes of the previous blocks if the previous blocks have not done any of the writes or do not have any writes to that variable, and it can reach the memory before any of the writes of the previous block reaches the memory. So there is somehow unbounded reordering. A particular write can reorder with unboundedly many writes in the earlier blocks, in some sense. But one good thing about the execution of these threads is that each of the blocks, the execution within each of the blocks is like either a TSO thread or a PSO thread. So these NTWs are like a TSO thread. These WB writes are like a NTWs are like the PSO thread, and the WBs are like a TSO thread. So what we do is, and if you remember, the PSO can simulate a TSO behavior. So the decidability is by reducing our cache-free reachability or alternation bounded cache-free reachability to reachability on a PSO system. This we do by executing these blocks as a PSO thread. But we have to be a bit careful here because a later block can depend on earlier blocks. For instance, if there is a write pending in the earlier block, this guy cannot simply simply send his write to the main memory. Or for instance, if there is a SF pending in one of the earlier blocks, none of the later blocks can start its execution till that SF is cleared. And if they read a particular value, they have to read the last value of the last write of whichever block performed that write. So essentially, there are dependencies between the blocks. So especially the later blocks depend on the earlier blocks. So what we do is we somehow have a manager like before, and we duplicate we duplicate the main memory for each of these threads, PSO threads that we introduce. And this manager is now responsible for copying the memory, copying the values from this duplicate memory to the main memory. So the manager moves the writes from this copy memory to the main memory. But he also ensures that the semantics is maintained. What are the semantics that is maintained? He also ensures that the WB does not overtake a WB. A later WB does not overtake a earlier WB. So he ensures that this WB has completed all its operations before this WB can start its operations. He ensures that the NTW on a particular variable does not overtake NTW or WB from an earlier block. For instance, this NTW cannot write to the main memory before all the writes to that particular variable in this WB is completed. Similarly, any NTW or WB cannot overtake an SF in the earlier block. So these are, among many other things, these are somehow ensured by the manager. There are many other things. The manager also has to ensure how the RMW is done and so on. But essentially, these are the more complicated things that the manager has to ensure. Yeah, I think I'm done with my talk.
Okay, thanks, Prakash. Are there any questions?
I have a question, Prakash.
Yes.
Yeah, thanks for the talk. So I'm just trying, first, is it possible to give some kind of sufficient conditions on the syntax of the program to ascertain that there will be at most k alternations between MTWs and
this is very tough. No, this is very tough, I think, because if there's a loop,
no, some sufficient conditions, not characterization. I'm saying some kind of useful sufficient conditions.
that will ensure that there is only so many alternation point. See, but there is a, okay, so I will not answer your question directly, but you see, this is somehow we are interested in catching bugs, right? So you can increase your alternation, you can increase your bound progressively to catch the bug. So as far as you want to explore.
I see.
But sufficient condition.
I see. No, I understand this kind of a restriction now. I see. Okay.
Yeah.
So do from okay. Yeah. Thanks.
Yeah.
So Prakash, I had a question.
Yes.
This undecidability result, I mean, isn't it, if you just take normal sequential consistent memory and even a single threaded program, isn't, can't you, isn't that also undecidable reachability?
So you have a sequential consistent program?
Single threaded. I mean,
Okay.
isn't that reachability
No, but
of a
sequential.
state there
No, but
also is undecidable, right?
No. Sequential consistency does not have a buffer. No, there is no infiniteness at all that is introduced.
No, I
So-
can just have a program that, guesses these I's and then verifies, that the UI is concatenated is equal to the VI is concatenated.
No, but you do not have a way to store these UIs and VIs, no? So,
But it's storing it in memory.
but memory is finite. So memory is just some finite number of variables, no? So here the problem is that here you have an unbounded buffer. Yeah, the buffer is unbounded in some sense that gives you the power, but that alone doesn't give you the power. For instance, the surprising thing is PSO plus PSO on their own is actually decidable. But once you combine these two, I mean, the undecidability sets in.
Okay. Okay, any other questions?
Maybe one more, Prakash, maybe this is to understand like this kind of this notion of persistency. One can also have it on top of any other model, right? I mean, I can have
yes, the persistency can be combined with many other, yes, what you say is true.
Okay, and what are the results, like in case you look at, sequential consistency plus persistence or RA?
So we have, in our previous work, we have shown that PSO plus persistency is decidable. Yeah, but this result, of course, I mean, generalizes it because this is a much more powerful TSO plus PSO with persistency. But I mean, it's actually an interesting thing to see when, or like what you said, a sufficient criteria when persistency can be combined with a memory model, and then you can get decidability. This is actually a very interesting question.
So, but RA plus persistency or SC plus persistency is not looked at yet?
AC for plus persistency, for instance, is already, yeah, from our result, it follows.
I see.
But RA plus persistency, I'm not sure. And so I'm not also sure how interesting it will be because, I mean, in this particular model, Intel implements it. So it is interesting. So, but RA plus persistency, I do not know if it is implemented and so
theoretically,
yeah, theoretically, of course, it is interesting. Yes.
Okay, good. Thanks, Prakash.
Yeah.
I have a question, but it's again more of a theoretical question. What if the buffer is lossy? In that case, does it still retain undecidability?
So buffer is actually lossy. If you think about it, buffer is not exactly like the way I presented, but you see what are these writes? Writes are something that goes to the memory and it never needs to be observed, right? In some sense. So I mean, you can make these buffers lossy by so if you take a classical TSO or PSO system, I mean, one of the decidability result is to go to a lossy channel system. So you can actually reduce this problem of reachability in a PSO or TSO to lossy channel system, reachability in a lossy channel system. So inherently, these systems are lossy because you cannot observe, a thread cannot observe all the memory that is presented to it.
Right. So, so if I don't remember correctly, but like TSO can be reduced to a lossy channel system, right? The reachability problem.
Yes.
I don't know about
Yes.
PSO, but I think I've read the
PSO can
part.
also be. PSO can also
I see.
essentially be reduced to. Yeah.
And it doesn't matter whether the buffer itself is now lossy or not, because it won't add to the.
Not immediately. I mean, you cannot.
see.
So the PSO can be lossy. I mean, the way the semantics that we presented can be lossy, but the TSO cannot be lossy for the simple for a simple reason. Let me tell you an example. Suppose I have a write. Suppose I have a write x equal to, suppose x equal to 0 and y equal to 0 is the initial memory that we started with, and there is a x equal to write x equal to 1 followed by y equal to 1 in your buffer. Then you cannot actually lose x equal to 1. Then what the configuration that you will reach is x equal to 0 and y equal to 1, which is not a valid configuration in the original system. So by the semantics that I explained, it is not lossy, but you can make it lossy. So the idea or trick is to actually encode, or instead of writing just the write, you can actually have a memory snapshot. You can in your buffer, you can actually have a memory snapshot. Then it becomes lossy in some sense.
I see. I think I get it. Thanks.
Yeah.
I'll think about it too.
So I guess there are no more questions. So let's thank Prakash. Thanks, Prakash, for a very interesting talk.
Yeah. So I'll go for my dinner in